Today we want to talk about linear functions as our kind of introduction to the way we're going to approach functions in this course. And what we're going to do is we're going to look at all different types of functions over a series of weeks. But today, focus on just the linear ones. And we're going to do a function analysis. And it's the way we're going to approach functions, and we're going to do 20 item analysis or 20 characteristics of each function. So the following 20 items should be addressed in each function analysis. So if you're assigned a function analysis, this is what I'm looking for, 20 items that you need to fill out for each one. Now, even though that sounds like a lot, many of the items are family specific. In other words, all linear functions have a certain set of rules that don't actually change between them. And so we're going to take a look with a linear example of y equals negative 2x plus 3. That's a real simple linear example. The first thing what we're going to do is we're going to write a function rule. And what is the equation of this function in proper notation? So f of x equals negative 2x plus 3. So all I've really done is it's already solved for y, so I replaced the y with an f of x notation. Now for the function rule, sometimes we do have to solve for y in order to get this to happen. So we can write an equation in standard form or in another form, point slope form, and it not be ready to just swap out the y's with an f of x. What is the parent function, or is our second item? What family of functions does this belong to? And I wrote linear, or f of x equals x is our parent function. What is the domain of this function? Now, all real numbers. The good news is this is one of those things that for linear functions, the domain is always all real numbers. However, the range is also all real numbers. Now, I will say there is, for the sake of linear functions, it's always all real numbers, with the exception of constant functions, in other words, horizontal lines, in which case the range is whatever that y value is. Remember that the range represents all the y values that could possibly be represented by that function. Continuity. Is this function continuous on its domain? And the answer is yes. For all linear functions, they are continuous on their entire domain. Is it increasing or decreasing, and for what interval? Now, linear functions don't change directions. So this one is a negative slope, so it is decreasing from negative infinity to positive infinity. It's decreasing for its entire domain. If it had a positive slope, then it would be increasing for its entire domain, and that's about it. It could be a constant function. In other words, it could be flat, in which case it would be neither increasing nor decreasing. What are the local maxima and minima? This never changes direction, so it has no maximum or minimum. It goes from negative infinity to positive infinity, and so there is no change in direction. What are the x-intercepts and the y-intercepts? Number 9, intercepts. So this one does have an x-intercept at 3/2, 0. It also has a y-intercept at 0 is 3, and this is in slope-intercept form, so it's pretty easy to tell that's at positive 3. Number 10, you should be able to find the values of a function for elements in its domain, which really just means evaluate the function. And we're going to do that by default for 3 elements in its domain. You can pick whichever 3 you want. I just happen to pick 0, 10, and negative 5. There's nothing special about where I got 0, 10, and negative 5 from. I just picked 3 random numbers. 0, because that's pretty easy. 10 and negative 5 give me a little bit of variety. I want to make sure I was going in both directions. And so if I plug those in, I get 3, negative 17, and 13 respectively. And that's all we need to do for this. So if you are filling this out for any other function, you just plug in whatever numbers you want. Transformations. We've talked about transformations in the past, but we'll go into more detail as we get into more complicated function families. For linear functions, there's not a lot going on. The parent function f of x equals x is a positive slope of 1. And so the first thing we're going to notice is that our function that we have for this example is a negative slope. So the first thing we're going to do is a vertical flip, and that makes it go, instead of going up, you flip it upside down, and now it's going down. The next thing we have is that instead of a slope of negative 1, it's actually negative 2, which means it's steeper than the parent function. So this is a vertical stretch. We've increased the steepness by stretching it vertically. The last thing is that we did a vertical shift. We took the whole graph, and it doesn't go through the origin, it actually goes up some. And we moved it up 3 vertically. And so we just shifted it up that way. Now, we just described the transformations, and now we can look at our function and go, you know what, that's exactly what it looks like. It looks steeper than the parent function, it's been flipped upside down, and it's also been shifted up. What is the end behavior as x approaches infinity? And what is the end behavior as x approaches negative infinity? So when we talk about end behavior, we look where x is approaching, so we focus on the x-axis, and then we say, where would the y's end up if the x's kept going to infinity? And if we look back at our function, as x's go to negative infinity, as x's go to the left, the function is going down, down, all the way down. No, because it's a negative. So as we go to the left, the function's actually going up into the sky. And as we go right, the function goes down. End behavior, as opposed to increasing, decreasing, you start from the middle and go outward. Increasing, decreasing, you go from left to right. And don't get those mixed up. Is this function even, odd, or neither? This is actually neither even nor odd. And even in an odd function, both of them would have to go through the origin, and this one does not. Does this function have an axis of symmetry? What is the equation of the axis of symmetry? There is not an axis of symmetry for this type of function. A linear function is not symmetric. You could argue that you could draw a line. It would have to be like at an angle that'd be a perpendicular to that, where you could just draw and fold it. If you folded it just right at an angle, it would fold in on itself. But we're looking for specifically axis of symmetry. This is more about how we're going to handle quadratics and also some other types of functions that have a vertical line of symmetry. What are the equations of any vertical or horizontal asymptotes? Linear functions do not have asymptotes. So the answer to all of our linear functions asymptotes analysis would be no asymptotes. Inverse. What is the inverse of a function? Now, our function was negative 2x plus 3, and we talked about that it was doing three things. But really, when we look at that x, what's happening to that x, in the order of operations, we multiply that x by negative 2, and then we add 3. When we do the inverse, we do the opposite in the opposite order. So instead of multiplying by negative 2 and adding 3, we subtract 3 and then divide by negative 2. The other way to do this is to go ahead and switch the x and the y value, and then solve that new equation for y. And what that would give us, it would give us f inverse of x is x minus 3 over negative 2. I want you to notice that it's not a negative 1 as an exponent there. It looks like an exponent, but it really is, that's the symbols. The f with a negative 1 superscript is read as the inverse of f. So the inverse of f of x is x minus 3 over negative 2. Some new vocab for you here, possibly one-to-one or injective. Those are actually synonyms that you can swap those words out. Is this function one-to-one? Now, what one-to-one means is that every x maps to a distinct y. So if I were to give you an x like 0, you should be able to tell me that, well, 0 as an x gives me a y of 3. However, if I were to give you a different x and you were to say, well, what do you get when you plug in 5? And you were to tell me, well, you also get 3 when you do that. You get 3 if you plug in two different x values, you get the same y. In that case, it would not be one-to-one. In this function, however, every time we plug in a different x, we get a different and distinct y, which means this is one-to-one. Or we're going to say injective. That's a word for one-to-one. Every x maps to a distinct y, so this is injective. Number 19, another vocab word, onto. And again, the synonym, the other word we can use is surjective. Onto is surjective. Don't get those two confused. Is this function onto? Now, what onto means is it covers all of the y's. In other words, there's no y in our codomain that does not actually get represented on our line. And so since this line has a minimum of negative infinity and a maximum of positive infinity, in other words, it goes all the way from negative infinity to positive infinity on y values, it actually does map onto all the y's in the real numbers. So this is surjective. Our last item is one-to-one correspondence or bijective. All this is to say is if our answer to the last two was yes, then it is bijective. Is the function both one-to-one and onto? This time it is, which means we say it's bijective. If it was one-to-one but not onto, it is not bijective. So there you have it. These are the 20 characteristics that we're going to talk about with functions when we do a function analysis. And the catch is that we're not going to have to do this for every function we deal with in this course, but I want you to be familiar with what each of these words means and what we're looking for on each one. Each one is actually pretty small, and they tend to lean on each other. So, for example, even and odd has a lot to do with symmetry. The transformations tell us a lot about our graph. Our zeros and our intercepts are really interconnected. Increasing, decreasing, extrema, values of a function, all of it is so interconnected that I want you to be able to move in and out of each one of these items. Take a minute to make sure at this point that you have not misunderstood any of these. Now I want to take a moment to look at a constant function. Technically that has a different parent function than a linear function because the slope is 0. So we actually don't have f of x equals x. It's actually f of x equals c. There's some number constant. So what we want to do is we want to talk about this particular one and look at what is common about all of our horizontal line functions. First, function rule obviously is f of x equals 2. We could say that just as simply that this line was y equals 2, but the function rule is f of x equals 2. The parent function, as I said, is f of x equals c. You could say f of x equals 0 or 1, and that wouldn't bother me. I generally think about it as f of x equals 0 as my starting value. The domain is all real numbers. You can see that every x value is valid. No matter what x value I use, however, I would still have a 2 for my range. So my range is just the number 2. Is it continuous? You bet it is. There's no holes or anything stopping it. It's not increasing or decreasing ever. It has no maximum and minimums. It's just flat. It has no zeros. It never crosses the x-axis, but it does have a y-intercept. The y-intercept is, as you might expect, at 0, 2. We're going to plug in some values. No matter what value of x we plug in, f of 0, we get 2. F of -5, we get 2. F of pi equals 2. It's a trick because we can't actually put those numbers anywhere, even the number pi, because there's no x to plug it into. So we end up with the same 2 each time. Now, transformation, I went ahead and said the transformation was a vertical shift up 2 because I was going on the assumption that we started at the x-axis, and so we moved up 2 from there. If you have something different, then that doesn't stress me out. But if you said something silly like it's been flipped vertically, well, flipping this vertically wouldn't actually change it much. It would look about the same. The graph is there. I went ahead and copy and paste that in for you. When you're doing a graph in this class, if you could sketch it and just make sure a lot of your key features are there, I want to highlight end behavior because up until this point, a lot of times we think of end behavior as being either going up to positive infinity or down to negative infinity. In this case, as the x approaches negative infinity, so if I start in the middle and go left, where does my f of x go? Where are my y values? And the answer is, well, they're still at 2. And the same is true if I go the other direction. So my end behavior doesn't go to positive infinity or negative infinity. My end behavior of this function on either side is 2. It is not even or odd. Remember that even though it is symmetric, even or odd functions would have to go through the origin. This is symmetric. It's actually symmetric across the y-axis or for any other vertical line. But we're not going to worry too much about the axis of symmetry for this line because every vertical line would make this symmetric. Since it goes on forever, we're always in the middle. Asymptotes. There are none. The inverse doesn't exist. Now this one's important. Why doesn't the inverse exist? Because if I were to swap out the y and the x, I would end up with an x equals 2. The opposite function is a vertical line at x equals 2. But vertical lines are not functions because they fail the vertical line tests themselves. So the inverse does not exist for any horizontal line. The inverse does not exist. It is not one-to-one because remember what one-to-one means. It means for every x, if I give you a different x, I get a different y. But every x gives me the same y, so the answer is no, it's not one-to-one. Is it onto? Does it cover all of the possible y's? Well, the only y I get is 2, so what if I wanted a y that was 3? Well, impossible. And lastly, since I said no to the last two, the answer is no. It is not a one-to-one correspondence. All right, I'm going to leave you with this. I'm actually going to throw these 5 examples at you. 1, 2, 3, 4, 5, A, B, C, D, E. And I want you to try to do the full 20 item analysis for each of these 5. I know that 5 times 20 makes 100, so that's like answering 100 questions for practice. But the reason I want you to practice these specifically is I want you to notice what's common about all 5 of these examples. There might be a way that you could write it in a table, so you can literally use one sheet of paper and just write function rule and then have a column for each of these functions and so forth. However you want to organize is fine, but yes, I get there's 100 problems to do here. They will repeat some of the same answers. One thing I want you to watch out for is that the first thing you're going to have to do is get the y by itself. So make sure you do that for number B, or letter B, and also practice problem E. All right, good luck. Zeros of this function. This is pretty easy to find out. To find a 0, what we want to do is we want to look for what number we'd plug in for x to get a 0 for the y value. The other place we look is that this would actually be the x-intercept is what it would end up giving us if we do that. So one way we can do this, we could plug in 0 for our y, or f of x, not in the x place, but in the y value, and then solve that function for x, and we get 3/2. The other way we can do this, we could graph that function and find out what that is.